So when you're dealing with reaction rates, you're really thinking about concentration of either reactants or products uh, in regard to the timing of the reaction. So a general rule or equation to think about is rate equals the change in, let's just say, concentration of anything. So that could be a reactant at the start of the equation. That could be a product at the end of the equation. We're just thinking about a concentration of something. And in chemistry, when you see these brackets around either a letter or a compound, those brackets always are referring to concentration. We'll usually use concentration units of moles per liter. And the rate, going back to our rate, so the rate is the change in that concentration, delta meaning change in concentration over change in time. Okay, so let's look at an example problem and put this reaction rate equation to use. So looking at our reaction rates review, I'm going to go to number 2 just for your reference. And it says at 40 degrees Celsius, hydrogen chloride gas will form from the reaction of gaseous hydrogen and chlorine according to the following balanced equation. And so we're using this equation, H2 plus Cl2 yields 2HCl. So this is the reaction we're going to follow. And we have a table with some times and some different concentrations of those different compounds as they proceed through this reaction. So let's jump down to the first question, letter A. It asks us about how quickly is hydrogen gas disappearing in the first 2.16 seconds. That's just an arbitrary amount of time. It could be any amount of time there, but we happen to be looking at 2.16 seconds. How fast is hydrogen disappearing? So in other words, as this reaction proceeds, you start with more hydrogen, and as it continues into hydrogen chloride, of course, more and more of this is going to disappear. So what we're wondering is about the disappearance of H2 in those first 2.16 seconds. Okay, so how would you find that? How would you figure that out? Well, we're going to go back to our rate equation, our reaction rate equation. And remember, rate equals change in concentration, those brackets, over change in time. All right. So in this case, it's going to be the change in concentration of H2, and it's asking about the first 2.16 seconds. So our change in time is going to be T minus 2.16 seconds. So that's our change in T. And what would we say for change in concentration of H2? We look to that table, and I've tried to draw it in here. You can also see it on the assignment page. When T equals 0 seconds, before the reaction starts, the concentration of H2 is 1 mole per liter. So in other words, that is going to be 1 mole per liter minus our new concentration, which at 2.16 seconds, you can see the concentration of H2 drops to 0.5 moles per liter. So that makes sense, right? So the H2 is disappearing. It went from 1 mole per liter down to 0.5 moles per liter. And then you just work out the math. Then it's no big deal. Then it would just be 1 minus 0.5 gives you 0.5 moles per liter all over 2.16 seconds. And that comes out to be 0.231 moles per liter per second. And that is a concentration over time. In other words, a reaction rate. For those other questions, for letters B, C, and D, it's just asking about the different compounds involved. And so you'd have to think about what's happening to not only H2, but also Cl2 and HCl, depending on if they're appearing or disappearing. You'd have to think through how that concentration is changing over time. Let's look at an example of a reaction that's going to require a little stoichiometry to figure out our reaction rates. So here's an example, and you can take this and run with it with those other questions that are similar. Let's talk about nitrogen and hydrogen gas when they mix to form ammonia in this reaction. So N2 plus 3H2 yields 2NH3. Okay, so let's say we wanted to know if N2 disappears at rate of 5.0 times 10 to the minus 1 moles per liter per second. We want to calculate the rate of reaction for everything else, for other reactants and the product. Okay. So how would we do that? If we only knew the rate of disappearance of nitrogen. Okay, so we know that rate. We know that if nitrogen is disappearing at a certain rate, these other compounds in the reaction need to change at a proportional rate depending on their stoichiometry numbers. So since we'll kind of think of it as a 1 in front of that N2, since we have 1 N2 for every 3 H2s, and as those react, they are causing the appearance of 2 ammonia molecules. So we need to keep those stoichiometric ratios in mind when thinking about the rates of change of these different compounds. So if we know N2 is this 5.0 times 10 to the minus 1, if I wanted to know how fast H2 is disappearing, since the ratio for H2 is 3 times that, in other words, H2 to N2 is, let's say, 3 to 1, then I know that I'm going to have to take 3 times 5 times 10 to the minus 1 moles per liter per second to figure out how quickly H2 is disappearing. Remember with scientific notation that times 10 to a negative means you're going to make that number one decimal space smaller. And so that's really 3 times 0.5 moles per liter per second. And that is going to equal 0. That equals 1.5 moles per liter per second for the rate of H2. Okay, and what about how quickly NH3 appears? Well, if we look back to our ratio, again, we know the rate for N2, that's 1, so it's going to be a 1 to 2 ratio. In other words, NH3 is a 2 to N2, 2 to 1, right? So in other words, we have to take that same rate, that 5.0 times 10 to the minus 1 moles per liter second, and multiply by 2 to get 1.0 moles per liter seconds for the production of ammonia in this case. Okay. Hope that makes sense. I hope you can take that and apply it to the other problem in that reaction rate set. It's a different reaction, but the same kind of math.